Good morning, everybody. I'm Siddharth Ray, and I will be presenting our work, SwiftQueue, optimizing low latency application with Swift packet queuing. This is joint work done with my collaborators and advisors at U Chicago. Low latency queuing models. Let's start with that. So low latency sensitive applications require low latency queuing models, applications such as cloud gaming and voice over IP. And L4S dual queue is one such popular technique. L4S dual queue has a clean separation for TCP traffic. It has one queue, which has only classic traffic, and it has a second queue, which is for low latency traffic. And L4S is being currently deployed across leading telecom vendors across the world. We have some examples from Verizon, Comcast, T-Mobile. This makes a promising case for L4S in use of production networks in the near future. So let's look at how L4S actually works. So L4S piggybacks on ECN, which is explicit congestion notification, and the ECN field in the IP header is actually used to choose the queue. The non-ECT traffic, which is a marking in the ECN field, is used to determine what is going to be sent in the classic queue, and everything which is marked as ECT1 is sent to the L4S queue. A notable difference is that L4S packets are marked as congestion experienced, and these packets are not dropped. And let's look at how this works in practice. At the sender, we have two possible kinds of packets marked for classic queues and packets marked for L4S queues. And in the vanilla L4S, packets marked for classic queues are always put in the classic queue, which are the orange packets. And packets marked for L4S queues are always put in the L4S queue, which are the blue packets. And this decision is actually made at the sender itself. And packets from the same flow are always put in the same queue in a static manner. So we ask the question, can we make smarter queuing decisions at the packet level by predicting the latency of the next packet or packets? And the idea is that we can reduce the tail latency by reducing the latency of the packets, which would experience high values of queuing latency. And these decisions need to be made at the sender before the next packet is sent out. And let's look again at the vanilla case where we have the standard L4S, and all packets currently are marked for Q1, and there is no change. And what would happen in our system of SwiftQueue if we could decide what packets could be sent to Q2 at the sender itself? And we can see that at the sender, we could make a decision to mark some of the orange packets as the blue packets and send it to the Q2. So if we can predict the packet latency of the next packets, we can assign queues at the packet level. But how do we leverage and use time series packet data to actually enable packet latency predictions? So packet latency values have some learnable signals. Learnable network signals are embedded in past packet latencies. An example, video applications such as Netflix can have periodic packet bursts of video chunks or frames within a session. And packet interactions from flows using certain TCP congestion control logics can result in learnable latency patterns such as queue buildup and backoff. Some latency variations, of course, are unpredictable, which are due to exogenous factors such as user clicks and link failures. And this work will not focus on such events. However, predicting packet latency is challenging. Packet interactions and joint queue buildup need to be learned, and these latency changes are caused by interactions on a shared network. Additionally, we need to predict latency changes, not values, because latency spikes and drops are what we care about, not predicting the average latency values over the entire trace. And simpler models for time series often fail at this, such as ARIMA models, and we need expressive models to actually learn these embedded signals. So we introduce the game changer model, which is the transformer model. Transformers are expressive models for time series predictions, and they use the attention mechanism to capture complex temporal patterns. And the attention mechanism enables greater memorization from past learned interactions, whereas other models from the deep learning, such as LSTMs, have been known to suffer from problems like vanishing gradients. And attention can also be parallelized, which reduces the need to process packets in sequence. This reduces the training and inference time for these models while maintaining prediction accuracy. So let's look at how a transformer model would work in the network case. So we have the latency values of multiple packets in a TCP flow, and we focus on two kinds of packets. One, after the latency spike, which is in blue, and there's also other packets which have latency values marked in yellow. And we can see that if we give the past values before the spike and other past values before non-spikes, these are actually mapped to very different positions in the TSNE visualization using the transformers intermediate layers. We can see that the latent features of high latency prediction is in a very different space from the latency features of low latency prediction. And the transformer maps different latency inputs to very different positions in the feature's latent space for learning and is able to extract these fine-grained signals. And we can also see that the absolute first packet, when the spike happens, can be predicted to have high latency. So knowing this, we introduce SwiftQueue, which is queue selection with packet level latency prediction. We have two components. First, we design and train a transformer for latency predictor, where we have different components to actually make this happen, which I will go through, which are fine tuning, change focus loss function, and expressive input features. Based on this, we have a queue selection mechanism for L4S, where we can assign packets to different queues at the sender, at the packet level, and we have other features to prevent queue oscillation and fast prediction with patching. So let's go over these one by one. So let's go over the change focus loss function. So the mean square error, which is generally used for training deep learning models such as transformer, does not focus enough on sharp changes as it is too smoothened. So we design a custom loss function which focuses on sharp changes, where if the change is greater than a threshold, and our threshold over our experiments are the value of plus minus 20 milliseconds and a 20% change, these values are selected from the fact that a change in 20 milliseconds is actually perceivable for low latency applications such as VoIP and cloud gaming. And the transformer is trained to predict sharp latency changes rather than just the average values. And this, of course, can be changed based on the nature of the actual application. And change focus loss functions are better at sharp change prediction than average value prediction, which is what we care about for this project. We also want to have fine tuning, which is fast, because we want to be able to adapt to changing network configurations. So we have a redesigned smaller transformer, which is around 100,000 parameters. And this is much smaller than the transformers we see for LLMs and other domains in practice, which have millions or billions or even hundreds of billions of parameters. And it can even go up to trillions of parameters for models such as GPT. And then we look at the packets in the context history window. And for pre-training, for learning the embedded signal, we train all of the transformer encoder layers. But for fine-tuning, we are able to only train the linear layers because the actual embedded information has been learned and the change can be embedded by learning just the linear, by fine-tuning just the linear layers. So fine-tuning on a reduced parameter set is enough if the network features have already been learned in the pre-trained process by the hold model. We also need expressive input features because just learning the future latency of packets based on past latency was not enough. So we have a small feature set per packet where we have the latency values if the acknowledgement has been received, and other features such as the timestamp, packet size, flow ID, and receiver ID. And every packet in the context history window has a set of features which is used to train or fine-tune the transformer. And the context history window size also needs to be contained to a size where fine-tune is actually efficient. And for this, we set it to match 1 to 2 times the maximum bandwidth delay product, which matches the number of recent in-flight packets, which captures the most amount of information from recent network history, which is actually useful for making predictions for packet latencies in the upcoming future. Looking at further history can obviously be useful, but over the course of our experiments and for the use case, we saw that this window is good enough for the application we have seen. And expressive models can learn packet interactions from much smaller feature sets because it is able to learn embedded information by looking at the interaction. Now let's move on to SwiftQueue queue selection logic. So we choose the queue per packet using the predicted latency, and we mark the ECN header in the field to select the queue for the L4S packets. And we focus on reducing the latency for L4S queues. The classic queue is relatively less congested in this setup. Now we need to think about two problems which can happen here. One is preventing queue oscillation. So unacknowledged packets may actually cause unstable queue selections if they're not part of the queue selection decision, because sometimes we do not receive the acknowledgement for a packet in time, but we need to make the prediction for the next packet to be sent out. So for selecting the queue, we also use the information for past unacknowledged packets, but whichever queue they were decided to be put in by the predictor. So we can see over here that we have the acknowledgements with the latency values for packets up to 5, but we also have sent out packet 6, 7, 8 for the queue. So for choosing the queue for packet 9, we also take into consideration the decision of the queue selection for packet 6, 7, 8. Secondly, we need to make the prediction in time because network latency is a bottleneck. And for inference might be a bottleneck for network latency. And if you're not able to make the prediction in time, this will slow down the network. So we do this by making a prediction for the future batch of packets. So we look at this illustration that we have the acknowledgements over here from packets 1 through 5 with the latency values. And we also have the unacked packets for which the queues have been selected. We don't make the prediction for packets which are immediately after this because that will not be in time. So we make the prediction for a future batch of packets so that the prediction is in time for queue selection and sending the packets out in time for the application. Now, this comes with a trade-off for batch size versus quality, because the more we predict into the future and larger batch sizes we predict, the prediction quality also goes down. The best prediction quality is obviously at the batch size 1, and this is the trade-off, which we will explore in our evaluation. And the latency for packets 12, 13, or 14 are the ones in the predicted batch when we are making the prediction at packet number 8. So let's look a little bit at the evaluation. For this, we collected real-world traces. We collected 2 different kinds of applications on 2 different kinds of endpoints. We collected video and web traffics, both on Wi-Fi and Ethernet endpoints. For video, we had the Netflix application. For web, we had the Facebook traffic application. We collected the trace duration for 30 minutes, and this is the distribution of how the flow duration looks and the number of flows in the trace. While this is good for predicting the performance of the transformer on its actual prediction latency performance, we also need a setup for actually making the decision for L4S queue selection. For this, we have an NS3 simulation where we have a sender and a router and a receiver, and the router has 2 kinds of queues, which can receive both classic and L4S flows. And the traffic sent over here is trace-driven simulation by replaying the actual traces we collected from video and web traffic on both of these endpoints. And the prediction is made at sender 1 before sending out the packets to decide which packet should be put in which queue. So let's look a little bit at the end-to-end result. So first, we look at the prediction performance of SwiftQueue's transformer, and we compare with 2 baselines. One is an LSTM baseline, which is another deep learning model, and one is a classical machine learning technique called XGBoost. And we see that we have much higher precision and recall over all kinds of traffic, so I have a superior prediction quality on sharp latency changes, which is the figure on the top. The blue bar is our SwiftQueue-based transformer, the red and green are the baselines. And then we see that the prediction quality is much superior. We also see by making the choice using the predictions of the L4S for SwiftQueue's transformer on L4S, we are able to reduce the L4S tail latency. So we see that we have 45 to 65% higher latency change prediction, which is better than the baselines, and 36 to 45% P99 latency reduction as compared to the baselines. We also want to explore the evaluation on efficient fine-tuning for SwiftQueue. So first, we look at the case of increasing the fine-tuning interval, because setting the fine-tuning interval is one of the parameters which decides how efficient our system is. So across experiments and across all the traces, we saw that 5 minutes was a good fine-tuning interval. What this would mean is that at every 5 minutes, we would fine-tune on the previous 1 minute of the trace and then evaluate for the next 5 minutes. And then we would repeat this procedure for the entire portion of the trace. And we tried this with different fine-tuning intervals. Of course, we need to do more research on how to find a systematic way to decide fine-tuning intervals, but the choice of the fine-tuning interval is part of the deciding the actual efficiency of a model like SwiftQueue. We also want to look at the evaluation on the batch size, which I had spoken about earlier, because having a higher batch size is better in terms of making the prediction in time. But as we see at a batch size of greater than 8, the prediction quality starts to suffer. The best quality, as I mentioned, was at the batch size of 1, but over here, the prediction cannot be made in time. So we reached a good trade-off at a batch size of 8, where the prediction quality was good enough to achieve good tail latency reduction, or by also making the predictions in time for real ISP network speeds of 200 Mbps on the link. We have more results in the paper where we perform sensitivity analysis, stressing the predictor performance, where we change the number of flows in the system, we change the link delay, we change the queue sizes, and evaluate the robustness of SwiftQueue's transformer predictor across these setups. We also have further ablation studies on the loss function. By using our loss function is better than using the standard mean squared error. And we also have ablation studies on different TCP congestion control algorithms running across flow interactions and measuring the predictor performance across them. So in conclusion, we would want to iterate that We are the first transformer-based packet-level sharp change value predictor for use in networks. And we achieve L4S. For L4S, we achieve packet-level queue selection to mitigate high tail latency for latency-sensitive flows. Thank you.